Okay, so good morning everybody. As Brian said, Hussein couldn't be here, so 3 days ago he asked me to come and give this presentation, hence my name now appears on the first slide. He didn't really tell me that it was the first presentation. He neglected to give me that piece of information. But anyway, I'll do my best to fill in his shoes. So what we want to talk about today is a project that we ran to migrate our GPFS file system infrastructure from one location to another location. So this year CSCS moved to a new building in Lugano proper, and it's some 3 kilometres geographical distance. The new site is from the old site. The dark fibre distance is 10 kilometres and the road distance is 6.7. We've got a little picture here. You can sort of see the old building there on the left-hand side. And we go across and over a hill and down into Lugano to the new site. So, it's a typo there, sorry for that. When you move your entire HPC infrastructure from one data centre to another, there's a whole bunch of things you have to consider. You've got all the various systems, you've got the network, you've got the other IT infrastructure, and most importantly, you've got all your user data that you keep at the site. So the question arises, how will you move this data? Do you back it up onto tapes and do it that way? Do you power the disks off, move them, and then power them on again? Or do you try to move the data online? So obviously all of those different options have pros and cons. We wanted to try and minimise the disruption to our user community. There was going to be enough of a disruption as it was, with the main supercomputers being down for 3 weeks or so, and we wanted to allow the users to carry on working if possible. So the only option that made any sense to us really was to move the data online. So we have multiple file systems that are global or site-wide. There's 4 in fact, and there's several petabytes of data there. There's a large number of files and a bunch of other dependencies and so forth. I'm not entirely sure what he intended to say about the rest of those points there. This slide gives you an indication. This is the layout of one of the large site-wide, or we call them global file systems. It's what we call a project file system. There's a lot of detail in the slide, but really the main point of the slide is to indicate that the storage infrastructure is modular. So by that we mean that we have storage hardware like disks, enclosures, controllers, and servers all grouped together in racks in a modular fashion. So this gives us, I think, a nice way to consider the file system in this modular fashion. It means that when you start wanting to migrate, you can use the features of the file system. Like, for example, with GPFS, you can migrate the data from some of those NSDs onto the other ones. Once all the data's been moved, then you can power down one of those complete modular racks, move the hardware, power it up, confirm that the drives come back online and that they've survived the trip. Disks don't usually like to be shut down and put in a truck and jiggled around and so forth, so it gives you the opportunity to make sure that once the hardware has been moved, it's all okay and ready to receive the data, and then you can start moving data to that hardware in the new location. This slide basically summarises what I've already said. We've got 33 million, well, we had 33 million inodes in that file system. It's GPFS 3.4. It's all based around Infiniband QDR network infrastructure and these other file systems as well. So they use as home directories, a global file system for applications that are used across the various systems. And we also have a data repository, which we've called the store file system, which replaces a legacy archive backup system that we had. And this, in fact, is a slide showing the store file system. It, again, is modular in nature. The project file system's based around IBM and LSI hardware, whereas this one's based around DDN hardware. But there again, it's modular in nature. This slide shows our old CSCS Infiniband network. I think it's a fat tree topology. Really, the purpose of this slide is to show you what schematically the network looks like and give an indication that somehow, if we're going to use a range extending technology to extend that network, we have to find somewhere to shoehorn it in to that infrastructure. I'll show you a slide later where you can see how we did that. So I'm not sure how many products are available on the market to allow you to extend the Infiniband network from one geographic location to another one, but the guys reviewed what was available and decided that this Obsidian longbow technology was the way to go. So we chose a system that has 4 SDR IB links, and it is able to cope with this 10-kilometre range. It supports RDMA and has high availability built into it. So the key thing there is that there's 4 SDR links. And you probably can't see this very well, but we set up a test infrastructure because obviously we wanted to try and get an idea of how this would actually work. So in the middle there, we set up basically a spool of fibre, 10 kilometres worth of fibre on a spool in a 6U unit, I think, and put it in a rack. And then at one end of that 10 kilometres of cable, we put some storage infrastructure that was emulating the Lugano site. So we had some NSDs there and some DS5400 Pikes Peak controller and some storage. And at the other end, we had a similar setup with DS5300 storage, some storage servers and QDR switches and so forth. And the idea was that we would run a series of benchmarks, this OSU benchmark, the RDMA OFED performance tools, IPerf tool, and try playing around with GPFS to add and remove NSDs. And they spent, I think, several months playing around with these tests. The results, I think, were pretty good. The RDMA bandwidth test for the Mellanox QDR is on the left there, and you can see that this saturates at the 3.2 gigabytes a second. So then they ran the same RDMA bandwidth test over the Obsidian technology, and the graph on the right shows the bandwidth that was obtained for one of the 4 links. So you can see that it saturates at about 800, so 4/8 of 32. So basically we're able to saturate those links and get QDR performance, which I think is good. They also used the latency tests to test the latency. So on the left again you see the Mellanox QDR latency, and it's very low. The scale there is microseconds. So, and on the right hand side you can see the results from the Obsidian test infrastructure. The thing to note here is that the latency has increased from some value less than 5 on the left to some value a little bit more than 50 microseconds. But when you consider the physical limitations like the speed of light, I think the speed of light means that you have a latency of roughly between 3 and 5 microseconds per kilometre. So most of that 50 milliseconds is due to just the physical limitations of the speed of light. So it seemed pretty clear from that the Obsidian technology wasn't putting any major overhead on the latency. We also ran this IPerf test. Can't remember what he wanted to say about this. Basically, this 9.2 gigabytes, and we were getting close to 8 gigabits a second. I'm not sure if you can see this very well, but the point of this graph was really to show, what did they say about this? That all the links were seeing the same sort of traffic during the tests, so that one link wasn't lagging behind in some way, that we were saturating as much as possible all 4 links at the same time. And the purpose of this slide is to show that really the traffic was indeed parallel. So all of these graphs stop at exactly the same time. So that gave an indication that things actually were happening in parallel, and it wasn't like one link was out of phase with another one. So this was how we proposed, and in actual fact I think this is the actual topology of the network as we have it at the moment, between our new data centre at the top and the old data centre at Mano at the bottom. So this, because of the topology and the fact that the range extender is in the middle there, we had to change from a fat tree infrastructure or topology to an up-down by the mere fact that we've got these other nodes at different levels because of the range extender. The new site is our default site now, and the old site will be shut down in a couple of weeks' time, and then we can switch off the range extender. We don't need it anymore. At the moment, we've got production and backup Meteo Swiss systems at the old site, which need to stay switched on until the end of June, and then we can decommission all that equipment and sell the building, the old building. So those slides were basically what we measured with our little test infrastructure, and now I can show you some graphs of what we actually measured when we were doing the production migration, because on the basis of the tests that we ran, we thought that this technology was well suited. And so what we see here is slightly different from what we saw with the test infrastructure, and really the key point here is that the migration was taking place. So data was being migrated from some NSDs at the Mano site to other ones at the Lugano site, but at the same time the file system was in production. And so we see here in these graphs we have like a background migration of the data happening as well as user load, because users could have been accessing files that were in actual fact at the remote site, at the Mano site, and that basically meant that we didn't see exactly the same saturation of the links as we did in our little laboratory tests. This graph, Stefano gave me this just to show the production IOPS for the file system stayed consistently around 5,000, which he said isn't a huge number, but it basically shows that the file system was just working as hard as it could, I think. So there were a few lessons that we learnt from this whole exercise as you do. You know, the more you do something, the more you learn. The key things really were that we needed to avoid certain things to do with GPFS policy engine, like snapshots, because we do daily snapshots for all the file systems, and we discovered that if you ran those snapshots, it caused some very long hesitations and pauses in the file system, which obviously wasn't good when we were trying to allow the users to stay in production, especially for the user's file system, because that's where the home directories are. If you try to log in and the home directory file system is stalled, you can't log in. So users don't like that. We also turned off the TSM backups because that also caused some problems. And as I alluded to in one of those earlier slides, the fat tree topology breaks as soon as you put in this range extender, and you have to move to an up-down topology. I'm not sure what this LMC 4 lids per HCA, I can't remember what Hussein wanted to say about that. I think it was something about link aggregation. And it seems that the OpenSM may actually allow some different routing in the future. So that's really all I have to say. We wanted to thank our network specialist, Chris Gamboni, and our storage specialist, Stefano Guarini, who takes care of all the GPFS infrastructure, and Thomas Schoenemeyer, who is Hussein's boss, and he took care of the project management for the project. So, any questions?